Hello everyone. In this particular video, I am going to discuss pentahalides of group 15 elements. In my last video, I had discussed trihalides of group 15 elements. So, do you think like trihalides, all the pentahalides of group 15 are known? The answer is no, because all the elements of group 15 do not form pentahalides with all the halogen atoms. So, what are the pentahalides are known? Let's have a look. Fluorine, chlorine, bromine, iodine, nitrogen, phosphorus, arsenic, antimony, bismuth. Nitrogen do not form any pentahalides. Phosphorus forms pentahalides of fluorine, chlorine and bromine. Arsenic and antimony form pentahalides of fluorine and chlorine only. Bismuth forms only one pentahalide, that is bismuth pentafluoride. Okay, now my question is, why nitrogen does not form pentahalides? This is because nitrogen does not have vacant d orbitals in its valence shell, as it belongs to second period. Second period elements have only 1 twice s and 3 twice p orbitals. These 4 orbitals can accommodate maximum 8 electrons. It means the second period elements can accommodate maximum 8 electrons in their valence shell. But in case of pentahalides, there are 10 electrons around the central atom due to the 5 bonds. If pentahalides of nitrogen would have been exist, then nitrogen would have had to accommodate 10 electrons around it. But it is not possible. Let me consider an example. NCl5. In NCl5, nitrogen is forming, suppose, 5 bonds. 1 bond is equal to 2 electrons. 5 bonds equal to 10 electrons. It means 10 electrons around the nitrogen, but nitrogen cannot accommodate 10 electrons because it has only 4 orbitals in its valence shell, 1 twice s and 3 twice p orbitals. So how can nitrogen accommodate 10 electrons? That's why this compound does not exist. Not only this compound, all the pentahalides of nitrogen do not exist. Okay. My next question is, why pentaiodides of phosphorus does not exist? Why pentabromides and pentaiodides of arsenic and antimony do not exist? Okay. Though they have vacant d orbitals. Vacant d orbitals alone does not decide whether a pentahalide would be formed or not. There are 2 more factors that we should consider. These are what? Number 1, EX bond strength Number 2, steric crowding. To understand these two factors, let me consider two molecules of phosphorus, PF5 and PI5. In both compounds, the central atom is same, that is phosphorus. As the size of fluorine is smaller, therefore this phosphorus can accommodate 5 fluorine atoms easily. Without any crowding. But in this case, what happens, as the size of iodine is bigger, therefore 5 iodine atoms cannot be easily accommodated by phosphorus. These bigger size iodine atoms causes steric crowding, resulting in instability of the compound. And the second thing is bond length. What is the bond length? Internuclear distance between two atoms. Okay, look at the bond length. Here, the bond length between phosphorus and iodine is larger compared to phosphorus and fluorine. The larger the bond length, weaker the bond strength. It means less stable. Less stable means what? The compound does not tend to exist. That's why PI5 does not exist due to these two factors: weakness of EX bond and steric crowding. Okay. Similarly, we can say pentabromides and pentaiodides of arsenic and antimony do not exist due to these two factors. Okay, though they have vacant d orbitals. Got it? No problem. Next question is, why pentahalides of bismuth are not known except bismuth pentafluoride? In pentahalides, the oxidation state of central atom is +5. In case of group 15, the stability of +5 oxidation state down the group decreases. Okay, the stability of +5 oxidation state decreases down the group. That means from nitrogen to bismuth. But stability of +3 oxidation state increases from nitrogen to bismuth. It means bismuth does not tend to show +5 oxidation state. If it does not tend to show +5 oxidation state, it means it does not want to form pentahalides. Then why bismuth pentafluoride exists? Before going to answer this question, we should know about inert pair effect. What is inert pair effect? The valential electronic configuration of bismuth is 6s2 6p3. Okay, due to inert pair effect, bismuth does not lose its 2 6s electrons. It loses only its 3 6p electrons because 6s electrons are tightly held by the nucleus of bismuth due to the pore shielding of D and F as compared to 6p electrons. 6p electrons are loosely held by the nucleus of bismuth as compared to 6s. Therefore, bismuth loses only its 3p electrons. That's why it tends to show +3 oxidation state. So the stability of +5 oxidation state down the group decreases due to inert pair effect. Similarly, the stability of +3 oxidation state increases from nitrogen to bismuth due to inert pair effect. In case of bismuth pentafluoride, fluorine is so electronegative that it can forces bismuth to lose all of its electrons. Because fluorine is so electronegative, it is so electronegative that it forces bismuth to lose its all the electrons from its valence shell. Therefore, bismuth loses its all electrons towards fluorine, as it is more electronegative element in the periodic table. Chlorine, bromine, iodine, these elements are not so electronegative that they can force bismuth to lose all of its electron. Therefore, these pentahalides do not exist. Okay, have you got the answer? Next we discuss structures of pentahalides. Now I discuss structure of pentahalides. All the pentahalides have trigonal bipyramidal geometry in the gaseous phase. The central atom is sp3d hybridized. Let me discuss the structure of PCl5. PCl5 has trigonal bipyramidal geometry in the gaseous phase. Let me draw the structure. In PCl5, 3 PCl bonds lie at the plane of a triangle. The fourth PCl bond is lie above the plane, while the fifth PCl bond is lie below the plane. This is the triangular plane. Suppose these are 3 PCl bonds. Okay, they are making 120-degree angle. These all 3 PCl bonds are at 120-degree angle. This is the number 4th PCl bond and it is number 5th. They are lie at 180-degree angle. This means that these two bonds are not same with these 3 bonds. Why? Because these 3 bonds are lie at 120-degree angle, but these 2 bonds are at 180-degree angle. Therefore, we can say that in PCl5 all the PCl bonds are not equivalent. In PCl5, all the PCl bonds are not equivalent. As these three bonds are same, therefore they are called as equatorial. Equatorial bond. These three are called equatorial bonds, and these two are different from these three PCl bonds. Therefore, they are called as axial bond. Axial bond. Okay. The axial bonds are longer in length compared to equatorial bonds. Why? Because axial bonds are repelled by three equatorial bonds. Two axial bonds are repelled by three equatorial bonds. Two axial bonds are repelled by three equatorial bonds, while three equatorial bonds are repelled by two axial bonds. As a result, the axial bonds suffer more repulsion compared to equatorial bonds. So, to minimize the repulsion, these two axial bonds get elongated. Okay, these two axial bonds get elongated. Therefore, equatorial bonds are shorter in length, while axial bonds are longer in length. Okay. So, question is, why all the PCl bonds in PCl5 are not identical? Give chemical reactions in support of this. As the 5 PCl bonds are not identical, therefore on heating PCl5 we get PCl3 and Cl2, because two axial bonds are weaker due to longer in length, so they get easily broken when PCl5 is heated and give rise to what? PCl3 and Cl2. If PCl5 reacts with tin, then SnCl4 and PCl3 are formed. With silver, AgCl and PCl3 are formed. Balance the reaction, need 2 chlorine, na? So 2 silver. In this case 4 and 3, 5. Put 2 here, 10. It is 10. Essential for 2. 10 will not work. So put here 2. Okay. So 10. And these reactions support that all the 5 PCl bonds are not equivalent. Okay, no problem. Next we discuss Lewis acidity of pentahalides. Lewis acidity of pentahalides, especially pentafluorides and pentachlorides of phosphorus, arsenic and antimony behave as Lewis acid. As for example, PF5 arsenic pentafluoride, antimony pentafluoride, they behave as Lewis acid. In all these compounds, the central atom is bonding with 5 fluorine atoms. It means all the 5 valence electrons are involved in bonding. So they don't have any lone pair of electrons. So they do not behave as Lewis base. But they can accept a pair of electrons due to the presence of vacant d orbitals. Therefore, they behave as Lewis acid. Let me discuss some examples. As they are all Lewis acid, so they react with Lewis base. As for example, PF5, it is Lewis acid. So it reacts with F minus. All negatively charged species are Lewis base. It means this is Lewis base. The compound formed is PF6 minus. Similarly, SbF5, F minus, Lewis base, it is Lewis acid. The compound formed is SbF6 minus. Lewis acid accept the electrons donated by these Lewis base, and these compounds are formed. Okay. Next, we discuss hydrolysis of PCl5. PCl5 undergoes hydrolysis and gives rise to H3PO4 along with HCl. In this case, the oxidation state of phosphorus is +5. Therefore, it gives corresponding +5 oxidation state of phosphorus acid, that is phosphoric acid. The name of this compound is phosphoric acid. Okay. Balance the equation. Very simple. 5 chlorine. So put 5 here. Next 4 oxygen. So put 4 here. Okay. Next, PF5 does not undergo hydrolysis. Why? PF5 does not undergo hydrolysis. No hydrolysis products. Why? If it undergoes hydrolysis, then what products we could expect? We could expect H3PO4 plus HF. In H3PO4 there are phosphorus oxygen bond. There are phosphorus oxygen bonds. And in PF5 there are PF bonds. Now, which bond is stronger and why? Phosphorus fluorine bond is stronger compared to phosphorus oxygen bond. This is because the size of fluorine is smaller than the size of oxygen. Therefore, this bond is shorter than this bond. Shorter bond means stronger bond, and longer bond means weaker bond. So this bond is weaker, this bond is weaker and this one is stronger. So instead of giving weaker PO bond, better not to undergo hydrolysis. Okay, therefore PF5 does not undergo hydrolysis, otherwise it will have to form weaker PO bonds by breaking stronger PF bonds. So better not to undergo hydrolysis. That's why PF5 does not undergo hydrolysis. Similarly, PF3 does not undergo hydrolysis, but PCl3 undergoes hydrolysis. Why? Because it gives H3PO3. Here the oxidation state of phosphorus is +3. Here also +3. But PF3 does not undergo hydrolysis. Similar reason, weakness of PO bond compared to stronger PF bond. Okay, so pentahalides of group 15 elements is done. Next we discuss reactivity of group 16 elements in my next video. Thank you.